Hello, welcome back. In this practice video, we are going to focus on halogenation reactions of alkenes. We will review what happens when chlorine or bromine is added across a carbon-carbon double bond, and then we will discuss the reaction mechanism to explain two important observations. Why halogenation gives anti-addition and why carbocation rearrangements are not observed. As you work through these questions, try to predict the product first and then use the mechanism to justify your answer. Let's begin with the general halogenation reaction. An alkene reacts with chlorine or bromine, and one halogen atom is added to each of the two carbons that originally formed the double bond. The product is therefore a vicinal dihalide, meaning the two halogens are on neighboring carbons. In the example shown here, ethylene reacts with chlorine to form 1,2-dichloroethane. Bromine behaves the same way. Iodine is usually not used for this reaction because iodine addition is thermodynamically unfavorable and readily reversible. The key point to remember in here is that halogenation consumes the pi bond and forms two new carbon-halogen bonds. Now let's consider the bromination of cyclopentene. Cyclopentene is an alkene, and when you try to do the bromination reaction, you will observe the trans product only. You will not observe the cis product. So let's see why the reasoning behind that. So before looking at the mechanism, ask yourself why the two bromine atoms must end up on the opposite faces of the ring. If this reaction proceeds through a freely rotating open carbocation, we might expect bromide to attack from either side to produce more than one stereochemical outcome. The fact that the reaction gives anti-addition tells us that the intermediate must control which phase is available to attack. Here we can test a possible mechanism. Imagine that alkene first react with bromine to form an ordinary carbocation intermediate. In that kind of intermediate, the positively charged carbon would be approximately planar, so bromide would approach from either side. That would not explain why only the trans product is formed. Therefore, a simple open carbocation mechanism is inconsistent with the stereochemical result. This observation is our clue that halogenation proceeds through a different type of intermediate, one that blocks one phase of the molecule. The correct intermediate is a three-membered brominium ion. First, the alkene pi bond reacts with bromine. Creating a bridged brominium ion. Notice that bridging bromine occupies one phase of the former double bond and shields that side from attack. The bromide ion must therefore come from the opposite phase. As bromine attacks, the three-membered ring opens and the two bromine atoms end up on the opposite side of the molecule. This is anti-addition. For cyclopentene, that anti-addition gives trans 1,2-dibromocyclopentane rather than the cis product. Let's move on to our next question. The question is asking when 3-methyl-1-pentene undergoes bromination reaction with bromine in the presence of dichloromethane, why is product A is formed instead of the rearranged product B? So now let's apply the mechanism of bromination to our substrate 3-methyl-1-pentene. So when our substrate is undergoing bromination reaction, as the first product, it shows that two bromine atoms on the two carbons that originally formed the double bond. Product B shows that the carbon skeleton has rearranged. Before choosing, your answer asks, thus the bromination forms a free carbocation that undergoes a hydride shift or an alkyl shift. Keep the brominium ion mechanism in mind as you compare these two possibilities. Product A is formed because bromination proceeds through a bridged brominium ion rather than a freely rearranging carbocation. When the alkene attacks bromine, the brominium ion forms across the two original alkene carbons. Bromide then attacks from the opposite side and opens up that three-membered ring. Because there's no free carbocation intermediate, there's no opportunity for a hydride shift or an alkyl shift. Therefore, the carbon skeleton does not rearrange, and both bromine atoms remain associated with the two carbons of the original double bond. That gives product A. The broader rule is that bromination is anti and does not undergo carbocation rearrangement.